Hey, so picture this. You're drifting amidst the cosmic tapestry, stars illuminating the dance of the galaxies around you. And then in contrast, you spot a void, an area so dense, so deep that everything around it seems to get lost in its embrace. That, my friend, is a black hole, the universe's grand enigma. But let's ponder something truly mind-bending. These colossal voids, known for swallowing everything in their path, where even light cannot escape, could there be a scenario where they themselves could face demise? Could the universe's grand destroyer be destroyed? Black holes, the enigmatic giants of the cosmos. Alright, so black holes have been the stuff of legends, movies, and many a late-night talk. But to understand how they can be destroyed, let's see how they are formed. After all, to know where you're going, you gotta know where you came from, right? Black holes are not holes in the conventional sense, but a region in space where gravitational forces are so intense that nothing, not even particles, can escape. They are remnants of massive stars that have undergone a dramatic end in a supernova explosion. Imagine you have this ginormous star, way bigger than our sun. It's been shining bright, the heart and soul of its galaxy for millions, maybe billions of years. But stars, like everything else, have a life cycle. And for such massive ones, their end game is, well, pretty dramatic. You ever watch a fireworks show and there's that one big finale firework that just takes your breath away? Stars kind of have their own version of that. See, for most of their lives, these stars are busy cooking up a storm in their cores. They're like cosmic chefs, right? Their specialty, fusing hydrogen into helium. That's nuclear fusion for you. A kind of cosmic high five between atoms that results in a massive release of energy, transforming matter into power. But hey, every chef, no matter how cosmic, runs out of ingredients at some point. When these stellar giants run out of hydrogen to fuse, they don't just put up a close sign and call it a day. Nah, they put on the grandest show you could ever imagine, a supernova explosion. Think of it as the last encore of a legendary rock concert. It's dazzling, mind-blowingly bright, and makes you feel pretty tiny in the grand scheme of things. Isn't the universe simply fascinating, orchestrating a continuous symphony of cosmic melodies? But here's where the cosmic plot thickens. After that dramatic finale to mark the end of their life cycle, the remains of these stars start to come together, almost like they're huddling up for a grand encore. This isn't just any old huddle, though. It's like taking the mass of our sun, or even several times that, and squishing it down into a space as tiny as a city. Imagine compressing Earth with all its mountains, oceans, and skyscrapers down to the size of a marble, yet still having it weigh as much as the original planet. Mind-blowing, right? This creates an object so dense, it's as if you crammed all the information of a vast library onto a single microscopic dot. And with such insane density comes an equally intense gravitational pull. We're talking a force so powerful that absolutely nothing, not even light, which zips around the cosmos faster than anything we know, can escape its dark embrace. That's the grandeur and the gravity, pun intended, of a black hole for you. It's nature at its most mind-bending and ruthless. The edge of this black hole, that's the event horizon. It's like the point of no return. Once you're past that, well, let's say you're part of the black hole's collection forever. Yet for all their might and mystery, black holes aren't invincible. And that's where our story takes an unexpected turn, and on to the main question of this video. Once this star has blown its top and the stellar dust settles, giving birth to a hungry black hole, does this grand space devourer have an expiration date? Like, can something so mighty and ravenous ever meet its own end? Spoiler alert, the universe is full of surprises. Hawking's cosmic epiphany, the Leaky giant. You see, back in the day, our understanding of black holes was pretty black and white. We thought they were the ultimate traps, swallowing everything and giving nothing back. Then along comes Stephen Hawking, the brilliant physicist with an out-of-the-box perspective. During the 1970s, disco was king, flared jeans were all the rage, and physicists were deep diving into quantum mechanics and relativity, trying to get them to play nice with each other. The thing is, these two theories, They're like oil and water, not the best of buddies. While most of us were jamming out to the Bee Gees, Hawking was puzzling over black holes. He blended quantum mechanics, the rules of the super small, with general relativity, the rules of the super big, in ways no one ever had before. And in doing so, he stumbled upon something mind-blowing. Hawking was diving deep into black hole properties, especially the nature of their singularities, those mysterious theoretical points at their center where density goes to infinity and our understanding of physics just falls short. Now, while exploring the mathematical implications of these black hole singularities, he started playing around with applying quantum mechanics to their event horizons. Kind of like if you had two jigsaw puzzles, one of the ocean and one of the sky, and you tried to fit them together. In the quantum tapestry of the universe, the vicinity of black holes is like a bustling cosmic market, where the usual rules are tossed out of the window. Now, space might seem quiet and empty to our eyes, but it's actually teeming with quantum mischief. We have these cheeky virtual particle duos, particles and their anti-counterparts, constantly winking in and out of existence. But when they decide to have a little rendezvous near a black hole's event horizon, things get interesting. Instead of their usual dance and mutual goodbye, the black hole's monstrous gravity gives them an unexpected plot twist. One gets gobbled up, while the other, now free from its partner, becomes real and zips away. This cosmic escapade, dubbed Hawking radiation, is like the universe's quirkiest and slowest diet plan for black holes. Every time a particle darts away, the black hole foots the energy bill, trimming its mass ever so slightly, a nod to our pal Einstein with his famous E equals mc squared. A tiny nibble out of the cosmic behemoth. Over incomprehensible timeframes, this mechanism can lead to the complete evaporation of a black hole, albeit at a pace that's incredibly slow on the cosmic timescale. Initially, Hawking himself was dubious about these findings, but as the mathematical proof solidified, it became clear that this was a groundbreaking revelation. The cosmic tango, why black holes dance together. Imagine two majestic dancers on a vast cosmic ballroom floor. Now, these aren't your average Joes. These are gargantuan black holes, each with their own intensive gravitational groove. In the vastness of space, many things happen due to the intricate dance of gravity, and black holes are no exception. It's not that black holes are out there actively seeking a partner, but if two black holes happen to come relatively close to each other thanks to, say, random cosmic events or the way galaxies evolve and interact, their immense gravitational pulls can start to influence each other. This is the beginning of their tango. Once they get within a certain distance, they'll get caught in each other's gravitational dance, drawing them closer and closer. It's a bit like two whirlpools near each other in an ocean, slowly pulling each other into a mutual spiral. As they get closer, they orbit around each other faster and faster, releasing gravitational waves and losing energy in the process. This energy loss makes them inch even closer, spiraling more quickly until they eventually merge. As they begin their final approach, they send out space-time ripples. Just like when you skip a stone across a pond and watch the circle spread outwards, these black holes send out gravitational waves, warping the very fabric of space and time. It was good old Einstein back in 1915 who first predicted such waves might exist, but proving his theory, that took us a solid century. Fast forward to 2015, our tech had finally caught up with our ambitions. Enter LIGO, Laser Interferometer Gravitational Wave Observatory. With a little help from its European cousin, Virgo, it made a groundbreaking discovery. They detected gravitational waves from two merging black holes that danced their last tango about 1.3 billion years ago. It's wild, right? We felt ripples from an event that happened before even dinosaurs roamed the Earth. Now, about the grand finale, the collision. You might expect a colossal cosmic explosion given the players involved, but black holes merging, it's eerily silent, yet intensely violent. There's no bright flash, no grand fireworks, but the energy they release, oh boy, it's monumental. Picture this. During the final moments of their merger, They can radiate more power than all the stars in the observable universe combined. This energy is sent out as powerful gravitational waves. These waves, though potent at their origin, become whisper quiet by the time they reach us, needing instruments as sensitive as LIGO to even detect them as they travel across the cosmos, only to be picked up billions of years later by our instruments, letting us tune into a cosmic symphony that's been playing since time immemorial.